Imagine walking into one of China's most advanced semiconductor factories. The hum of machines fills the air, engineers move quickly from one workstation to another, and every surface gleams under bright, industrial lights. In the middle of this high-tech symphony sits a Nikon DUV lithography machine, a precision instrument worth hundreds of millions of dollars. This is the heart of the production line, the tool that imprints microscopic circuits onto silicon wafers, shaping the chips that power everything from smartphones to electric cars. Now, imagine that this machine suddenly stops, not because of a catastrophic breakdown, but because a single laser component, the kind you could theoretically replace in a day, has simply reached the end of its service life. Normally, engineers would call the manufacturer, and within days, a specialist and a spare part would arrive to fix it. Production would resume, almost as if nothing had happened. But today, nothing happens. Requests for support are delayed indefinitely. Every inquiry is met with under review. The factory floor grinds to a halt. Hundreds of engineers watch as an entire production line, capable of generating hundreds of thousands of dollars per hour, sits idle. A small, seemingly insignificant component has become the most expensive bottleneck in the factory. This is not alarmist talk or a worst-case scenario. It's a real, tangible vulnerability. And it's one that has been amplified by international export controls. A piece of equipment that used to be reliable is now effectively frozen in time, leaving highly skilled engineers powerless to act. For a moment, you can almost feel the tension in the room, the pressure mounting as the clock ticks, and every hour of downtime means millions of potential losses. This is where our story begins, at the intersection of high technology, international politics, and the race to control the future of semiconductors. To understand why a single laser component can paralyze a factory, we need to zoom out to the bigger picture, the global semiconductor chessboard. Since 2022, the West, led by the United States, has been trying to slow down China's rise in high-tech industries, especially semiconductors. Their strategy: hit the supply chain where it hurts most, the equipment, materials, and technologies that make cutting-edge chips possible. The scale of this effort is massive. Over 600 Chinese semiconductor companies have been added to the U.S. Entity List, meaning they can't easily buy critical tools or components from abroad. High-end machines, rare chemicals, and core design technologies are all restricted. In other words, Washington is trying to cut off the lifeline that keeps China's semiconductor industry alive. But here's the catch. The semiconductor industry is incredibly globalized. A single chip requires a web of suppliers, engineers, and materials spread across multiple countries. One nation acting alone can't fully block China's access. That's why the U.S. has leaned on its allies, pressuring South Korea to review each export to China individually, and stopping the Netherlands' ASML from selling its most advanced EUV lithography machines. Among these allies, Japan has been the most loyal enforcer. With its own high-tech industry and control over key equipment and materials, Japan plays a central role in the blockade. This makes what seems like a technical story, machines and lasers, a geopolitical showdown. Each delay, each stopped shipment, isn't just a factory problem. It's part of a deliberate strategy to slow China's technological ascent. In short, what happens on a factory floor is directly tied to global politics. A stalled machine isn't just a technical hiccup, it's a single piece in a high-stakes international game, where each move can ripple across billions of dollars, entire industries, and even national security. Now that we understand the global stage, let's zoom in on Japan's role. In March 2023, Japan rolled out a sweeping export control list aimed directly at China's semiconductor industry. It wasn't just a few restrictions, it covered 23 categories of critical equipment, including tools for lithography, etching, and deposition. In practical terms, Japan was trying to block China from accessing the machines that make advanced chips, especially those below 14 nanometers where every tool is critical and hard to replace. By July 2023, the rules tightened even further. Instead of a simple paperwork process, every export now required case-by-case approval. Each machine, each order, even a minor spare part, like a replacement laser, had to be declared separately. Chinese companies were forced to submit dozens of pages of technical documents, explanations, and schematics. And there was no limit on how long the approval process can take. A request today could sit under review for weeks, months, or longer. No one could guarantee it would ever be approved. The impact on the factory floor is immediate and painful. A single malfunctioning lithography machine can now bring an entire production line to a halt. Take a 12-inch wafer line as an example. Every hour of downtime can cost $500,000 to $1 million. Multiply that across a full production cycle, and minor delays snowball into major financial losses. What used to be a routine fix, a laser replacement, has turned into a bureaucratic nightmare. In essence, Japan's strategy is to transform functioning machines into piles of scrap without physically touching them. The goal is clear. By controlling maintenance and parts, they hope to halt China's semiconductor production. But, as we'll see, this high-stakes game underestimated China's capacity to respond and innovate. Faced with Japan's chokehold, China didn't sit still. Instead, it turned a potential crisis into an opportunity to strengthen its domestic capabilities. By September 2023, Shanghai Microelectronics had already launched its own gold bump packaging and testing lithography machines. These weren't just experimental prototypes, they were real, production-ready tools. 2 units alone could handle 20,000 wafers per month with a resolution of 2 micrometers and were mainly used for power chips in electric vehicles. The results were striking. Using these domestically produced machines, supply chains became faster, chip yield rates improved, and inventory turnover time was reduced by over a week. Chinese engineers showed that their machines weren't just replacements, they were better suited to the rhythms of local production, solving practical challenges that imported machines sometimes struggled with. By 2025, Shanghai Microelectronics had developed the SSA 800-10W model, capable of a 28-nanometer process under single exposure and reaching 11 nanometers with multiple exposures. The company replaced 70% of critical components with locally sourced parts and refined the optical system to submicron precision, solving long-standing problems like bubble interference in immersion lithography. Production data from Qingdao showed 28-nanometer yield rates of 82% and exposure uniformity above 98%. Performance standards no longer confined to labs, but achieved in mass production. In short, China's approach wasn't just defensive, it was strategic and forward-looking. Where Japan saw leverage, China saw gaps to close. By building homegrown alternatives, it reduced dependency on foreign suppliers and turned international pressure into a driver for technological innovation. One of the most critical pieces in semiconductor manufacturing isn't a machine, it's a material called photoresist. Think of it like ink for a microscopic stamp. It's what allows a lithography machine to transfer circuit patterns onto a silicon wafer with extreme precision. Without high-quality photoresist, even the most advanced machine is useless. For years, Japan dominated this market. Companies like Shinnu Chemical, Tokyo Oka Kogyo, and JSR supplied nearly all high-end photoresist used in Chinese chip fabs. In 2023, when Japan tightened export rules and suspended shipments of KrF photoresist, China faced a serious risk. Its production lines could stall simply because it lacked the right ink for its machines. But Chinese researchers didn't wait. Using cryo-electron tomography, a cutting-edge imaging technology, a team at Peking University mapped the three-dimensional structure of liquid-phase photoresist molecules with resolutions better than 5 nanometers. This breakthrough allowed engineers to understand the material at the molecular level and begin producing their own high-end ArF photoresist domestically. By 2024, companies like Nandanda Optoelectronics had launched multiple ArF products that passed verification from leading chip manufacturers such as SMIC. These photoresists supported process nodes from 14 nanometers down to 7 nanometers, meaning China could now produce advanced chips without relying on Japanese suppliers. This wasn't just a technical achievement, it was a strategic shift. A monopoly that once controlled China's semiconductor production had been broken. Suddenly, dependence had been replaced by self-sufficiency, turning a potential vulnerability into a competitive advantage. Where Japan tried to tighten the noose, China found a way to thrive. While Japan was trying to tighten control over China's semiconductor industry, it didn't anticipate one crucial factor: how much its own companies depended on China. For years, the Chinese market was a major revenue source for Japanese tech giants like Nikon, Tokyo Electron, and Canon. At one point, nearly half of Tokyo Electron's quarterly revenue came from Chinese customers. Every wafer machine sold, every component shipped, helped fuel growth and profits. With the new export restrictions in place, this flow of business began to dry up. Orders were delayed, sometimes canceled, and approvals for shipments stretched indefinitely. Nikon publicly lowered its revenue target for 2026 from 750 billion yen to around 725 billion yen, while its profit forecast almost halved. Tokyo Electron experienced even sharper swings. In some quarters, sales and net profits fell by 30 to 40% compared to the previous quarter. In other words, the very strategy meant to pressure China started hitting Japanese companies first. Factories on Japanese soil, which once thrived on Chinese orders, now faced shrinking demand. Departments designed to support exports suddenly had idle staff. High-stakes decisions on the factory floor became financial and logistical headaches, with lost revenue mounting by the week. This turn of events highlights an important lesson. In highly interdependent industries, geopolitical aggression is never one-sided. By trying to block China, Japan exposed its own vulnerabilities. The story isn't just about a frozen machine in China. It's about a global ecosystem where every action has a ripple effect, sometimes bouncing back on the initiator. Beyond machines and photoresists, there's a hidden power in the semiconductor race: rare earth elements. These are a group of 17 metals used in everything from powerful magnets to precision sensors, and they are essential for high-end manufacturing. China dominates this market, producing more than 60% of the world's rare earths and handling nearly 90% of the refining and separation processes. Without them, many advanced technologies, lithography tools included, simply cannot function. Japan, despite its high-tech industries, relies heavily on Chinese rare earths. Every year, it imports over 5,000 tons to keep factories running. This means that if export restrictions were pushed too far, China could retaliate by limiting rare earth exports. Suddenly, Japanese manufacturers would feel the pinch first, and the companies trying to pressure China could find themselves in trouble. The lesson is clear. Leading-edge manufacturing doesn't rely on a single machine or material. It's a complex chain of interdependent tools, components, and technologies. Cutting off one link may create delays, but cutting off too many could trigger a counterstrike that hurts the blocker. China's rare earth leverage gives it a hidden shield, ensuring that no blockade, no matter how strict, can fully stop its technological progress. This perspective connects the micro-level story of frozen machines and blocked materials to the macro-level strategy of global industrial resilience, showing viewers why the race for semiconductors is as much about politics and resources as it is about technology. So, what does this story teach us? Japan tried to turn China's advanced lithography machines into piles of scrap by restricting parts, maintenance, and exports. But China didn't just survive, it adapted, innovated, and accelerated domestic capabilities. From building its own high-performance lithography machines to producing critical materials like ARF photoresist, China turned external pressure into a driver for self-reliance. This isn't just a tale of machines and metals, it's a lesson in strategic resilience. When dependencies are cut, innovation rises. When a blockade is attempted, a well-prepared system finds ways to adapt. And in global industries as interconnected as semiconductors, the story never has only one side. Japan's actions created setbacks for China, but they also revealed vulnerabilities at home, highlighting the complexity of high-tech geopolitics. For viewers, the takeaway is clear. The race for technological leadership isn't just about speed or money, it's about control, adaptability, and foresight. Countries that master these elements can turn challenges into advantages, and industries that invest in domestic capability can survive even the harshest external pressures. If you want to stay on top of these fast-moving developments, subscribe to our channel and turn on notifications. We'll continue bringing you in-depth stories, analysis, and updates from the front lines of technology and global strategy. Because the world of semiconductors isn't just about chips, it's about the future, and it's happening right now.